I want to do something slightly different. I'm going to explicitly solve this problem from this book. Okay, so I'm going to solve problem number 25. It's a computational problem. I think that's really nice because, there's no one way to solve it. You could do a whole bunch of different methods computationally. But it's a central force problem, so I'm going to describe the problem and then I'm going to go in and do it. So the problem is a particle moving under a central force. The magnitude of the force in the r direction is this. I'll talk about central force in just a second. Negative k over r to the 5/2. That seems like a weird value, but it works out fine. Mass, to make things simple, it's a numerical question, so we have to have values for the numbers to plot things. M equals 1, k equals 1, L equals 1. What a coincidence, right? So we want to find the value of r that makes a circular orbit, so a minimum, where the potential is a minimum. And we can actually do that two ways. So this is my central force review right here. I have a video on central forces. But the idea is if I have two objects interacting through some force that acts along a line between them, then we can reduce this problem to a one-dimensional problem in just the r direction. So the first thing is we have this mu, which is the reduced mass. It's the product of the masses divided by the sum of their masses. We have L, which is a constant, but it depends on two things that do change, r and theta dot. So this is like angular momentum. So it is a two-dimensional problem, right? We're doing it in equivalent one dimension. And we'll do that two-dimensional problem. And so with that, you get the following equation of motion for the r direction. Mu times r double dot. This is like mass times acceleration. And this is like the real force right there, right? Negative u partial v with respect to r is the real force. And then this is your centrifugal force. That's really what that is. L squared over mu r cubed. And then you can also, if I want to convert this to a potential, I can integrate this term and I can get an effective potential, which is the actual potential, which we can get from the force, and this term, which is just the integral of this with respect to r, negative the integral of this with respect to r. Okay. We need to plot that. So I need to find the potential up here. So let's just do that. Let's find the real potential. So u, I'm not even going to call it r for real. It's going to say u. It's going to be negative the integral of f dr. So it's negative the integral of k r to the negative 5/2 dr. I like to write it like that because I can remember how to do things, right? So if I integrate, I'm going to, and this is an indefinite integral, and that works fine here. If I integrate, I'm going to add 1 to the power. So if I add 1, that's going to be negative. That's adding 2 over 2. So it's negative 3/2. So I get k r to the negative 3/2. And then I have to divide by that. So then when I take the derivative, I get it goes away. So I have a negative already. So I get 2/3 r to the negative k, and k is 1, but I'm not going to put that in yet, to the negative 3/2. Is that what I got before? I feel like that's right. Okay. So that's that. That's my u. And so now I can write my u effective potential. I'm going to plot that. Okay. So this plus that is u effective. And where would there be a minimum? Well, there would be a minimum. Let's just sketch it, right? It's going to look something like this. The minimum's down here. This is u effective as a function of r. And so the minimum is right there. But what's true about the minimum is that the slope is 0. And if the slope is 0, that means the force, the effective force, is 0, right? Because the force is the derivative of u with respect to r. But I don't need to take the derivative. I don't need to integrate and then take the derivative because I already have this. I already have my one-dimensional equation of motion. This says the force, if r double dot is 0, it's at the equilibrium. So I can just say r double dot 0 and then solve for r. And I already have the partial negative, the partial of u with respect to r. It's this. So there you go. Okay. Now I'm thinking, wait, negative negative of the partial of u with respect to r. Oh no, this is just the force. Okay, so let's do that. Let's put these two things together. Let's solve for r0, and then I'm going to make a plot and show that we get the same thing. Okay, so I'm going to say, let me write f is negative k over r to the 5/2, and then mu r double dot equals L squared over mu r cubed minus, or the partial with respect to that, which is going to be plus k over r to the 5/2. Now, I guess the first thing we should do is find mu, which is pretty easy. The problem says a particle of mass. So if a particle, it's like the other object has an infinite mass, I guess. No, well, I think the main thing is mu is just going to be m1. I'm trying to think if the reduced mass, yeah, that's true. Yeah, mu is just m1. And then I'm going to set r double dot equal to 0. So that's going to be equal to L squared over mu r cubed plus k over r to the 5/2 is equal to 0. So now, oh, this should be negative. I'm sorry. F is negative. Negative. It is negative. Add the force, negative. So now I'm going to add that to both sides. I get k over r to the 5/2 equals L squared over mu r cubed. Now I'm going to multiply both sides by r cubed and divide both sides by k. I get r cubed over r to the 5/2 equals L squared over mu k. Now this, I can just write that as r to the negative 5/2 and put it up top. So I have r to the 6/2, r to the negative 5/2, and that's going to be r to the 1/2. And so now if I want to solve for r, I just need to square both sides. So this is pretty easy. R0 is going to be L to the 4th over mu squared k squared. Now I'm going to put in my values just to show that it's pretty easy. L is 1, mu is 1, k is 1. So it's going to be 1 to the 4th over 1 squared times 1 squared, or 1. Duh. Okay, so now let's go ahead and make this plot of the effective potential. And the textbook says go from 0 to 5r0, so to 5. So let me write down, did I write down my effective? Let me write down the effective potential. U effective, and this is the Python part, this is the fun part. It's going to be U of r, which is this, 3/2 k r to the negative 3/2, 2/2, 2/3 k. Is that should be negative? No, it's not. It shouldn't be. I think that's right. R to the negative 3/2. Everyone makes mistakes with negative signs. If you make a mistake with a negative sign, that's just like saying, hey, you're a human. Okay. And then I had the effective part of the potential, which is this, L squared over 2 mu r squared. So I'm going to plot this. I'm going to plot this from r equals 0 to r equals 5r0, which is just 5. Okay, let's jump over to Python and make this graph. This is really the fun part, I think. And so, of course, I'm going to be using web-vpython. That's what I do. I will give you the code. That's also what I do. So here we go. Let's start off with a graph. G1 equals graph. Title equals Taylor chapter 8 number 25. What do you think about that? X title equals R, and we don't really have units in this problem, so I'm not gonna pretend like they're meters or whatever. I'm just gonna say R. And then the Y title is going to be energy. We're applying the potential energy, but it is an energy. And let's give it a width of 400 and a height of 200, and that's that. Let's make that a little bit bigger. People like big, right? Everyone likes it big. Move this over here. Now I need to make a curve. I'm going to call it FU for potential, and it's a G curve. Color equals color.blue. I like blue. Blue just turns up nice. So now I need my values. I'm going to say L equals 1, which I hate because that looks really bad right there. That looks really bad, but I did it anyway. K equals 1. I'm going to call mu M. I don't want to type mu. Mu equals 1. What else do I need? R equals 0. I'm going to change the value of R. So now I need to pick. How do I change the value of R? Well, I need to pick a step size. Let's pick dr equals 0.1. And we can change that and make a better graph later. That's how big my step size is going to be. So what I'm going to do is calculate the effective potential, and then I'm going to move R and do it again, and each time I'll plot it. And I think that instead of just saying plot this thing, understanding what you're actually doing I think it helps. I like it. And we could even make a function for the effective potential, but I'm not going to do that first. I'm going to do it at least this way. So let's do this. While, I love while loops, R is less than R max. And what's R max? I never defined it. So let's put R max equals 5. Let's just say it's 5. And I know that's dumb, but that way I can change R max and it just makes me feel a little bit better. So now what I want to do is calculate the potential. So I'm going to say UE for effective potential. Now I have my equation. I'm just going to type my equation. See? It's an equation. Right there. So I'm going to say 2/3 times, don't worry if you have too many parentheses, don't worry about that, times R, which is a variable, raised to the -3/2 power. And that looks whack, but it's okay. It works fine. Plus L squared, make sure that's an L, not a 1, even though L is equal to 1, which is kind of weird, but divided by 2 times M times R squared. Now I'm going to plot that value. So I'm going to say FU.plot R UE. Now the most important point, if you don't forget this, your program will go on forever. R equals R plus dr. So I need to increment my value of R and then go do the whole thing over again. Let's see if this even works. Who knows? Could have had an error. Errors happen. Run. Okay, so that is not right. Let's see if this should be, if this is minus. I was right. Is that minus? No. Why is that not right? The effective potential. Let's see, so is the effective potential is L squared over 2 mu L squared over 2 mu R squared. That's right. And then U is the integral. So U is negative the integral. So, but I did it both ways. So it's either this negative the integral. L squared over 2 mu R squared. Negative the integral. I'm just checking my work here. So I integrated KR to the -5/2. I got KR to the -3/2 divided by -2/3, and then took negative that and I got a positive. Let's just try this. That's what I had before. Let's just change this to 2. Let's try this. Let's try a smaller step size. Oh, I think I know what the problem. One of the problem is. Let's not go from 0. Well, 0 is exploding because R goes to. We're dividing by R. So let's go from R equals 0.5 to 2. That looks a little bit better. Let's go to 5. See, it should have had that max, the min in there. Let's try this negative. Now I'm just randomly doing stuff. I'm going off the. There it is. Okay, I did lose a negative sign. Arg. Okay. Negative sign problems happen all the time. But see, how did I know I was wrong? How did I know it was wrong? Because I knew that there had to be a minimum in that potential to calculate, to have a central force orbit that's circular, because R double dot would have to be 0. That's where that would be. So let's increase this to 4. I want to make it look a little bit better. Okay, that's good. And you'll notice right here, at R equals 1, it is indeed a minimum. 1.01, that's fine. Okay, so I'm pretty happy. Number one problem was that I went too close to r equals 0 and it blew up. Number two problem, I missed a minus sign. Okay, but other than that, I got it. I got it. Okay. Next part was if the energy is equal to negative 0.01, find R minimum. We can actually get this from the graph. Okay, so remember that that energy is kinetic plus potential, and here's the potential. So if I have this is 0.01 right there, that's my negative 0.01 negative 0.1 energy. I'm pointing at the screen; you can't even see it. Let's draw this on paper. I think it'll be a little bit easier to see. Okay, so here's my sketch of my graph. So it looks basically like this, like something like that. And I'm down here. Let's see, put it up here. Here's negative 0.1. E equals negative 0.1. So the total energy is kinetic plus potential. Now, that means at any point right here, that's the total energy. That part is the kinetic energy, and that's the potential energy. And they have to add up to this. And you'll notice that the kinetic energy has to be positive. It has to be positive. What happens right here? Well, the total energy is the potential energy, right? Because they're right crossed over each other. And the same thing right here. So these are going to be the turning points. This is the minimum position because it can't go, if it was over here, it would have to have a negative kinetic energy. And that would mean an imaginary velocity, and you can't do that. So this part where E equals negative 0.1 crosses that is my turning point. Now, could we find that value of R minimum? Not super easy, right? Because let's write my potential right there, which is wrong. So U is negative 2/3 K R to the negative 3/2 plus L squared over 2 mu R squared. Now, if I want to say this is equal to negative 0.1, I can do that. And even if I put all my values at 0, at 1, so this is 1, that's 1, that's 1, that's 2, then I get negative 2/3 R to the negative 3/2 plus R to the negative 2 equals negative 0.1. And that is not an easy equation to solve. It's really not. But we did. If we want to solve it graphically, we can. We could solve it numerically, or we could solve it graphically. And the best way, I think, to solve it is to just look at the graph. And we'll do that. Okay. So let's just estimate the value of R min from the graph. R min is going to be going. I'm just switching over here real quick. I'll write it down. I'm going to say R minimum is 0.672. Okay, so that's part B. Part C says make a plot for R minimum at R starts at R minimum and theta is equal to 0. And then make a trajectory plot. So let's make a trajectory plot. We got a little bit of work to do here. Okay. Because we've made it equivalent one-dimensional problem, but it's not. So let's go back to our actual equation. Mu R double dot equals L squared over, where did I write it down? Right here. Where did I solve it? Right here. L squared over mu R cubed minus K over R to the 5/2. Yep, that's right. Okay. So that's our equation for R double dot, right? R double dot's not going to be constant now because we're not at R0. So let's just solve for R double dot. R double dot is going to be L squared over mu squared R cubed minus K over mu R to the 5/2. So what I can do is to break the motion into super small steps of time. T equals 0, delta t, let's try 0.01. During that time, I can assume that r double dot's constant. So if r double dot's constant, and I know the initial r is 0, let's just say it starts at 0, so r, let's call it r1 equals 0, I can find, and r1 dot is equal to 0, r2 dot, the velocity, is going to be r1 dot plus r double dot delta t. So this just comes from the definition of r double dot as delta r dot over delta t, and I get this. So if I know my initial velocity, which I'm going to pick as 0, after some short time interval, I can find r2 velocity, the velocity at the end of the time interval. Now I can do the same thing with r. r equals r2 equals r1 plus r2 dot delta t. And this is your basic numerical calculation. But that just tells me how r changes. What does theta do? Well, now I can go over to my definition of angular momentum. L equals mu r squared theta dot. That had to be constant, right? But now if I know r, let's call that r2, I can find theta 2. So theta 2 dot 2 is going to be equal to L over mu r2 squared. Now if I know theta 2 dot, I can find theta 1. I can find theta 2. It's theta 1 plus theta 2 dot delta t. So now going through this whole thing, I can update r and theta. And remember, we're like this. So that's r and that's theta. Now, if I want to make a trajectory plot, I actually want to convert that back to x's and y's. So I can say x equals r cosine theta, y equals r sine theta. So we're going to do all this in Python. Let's do it. I'm going to use the same program so I don't have to change. I'll just make another graph. We'll do it as a graph. Let's comment. Oh, I didn't switch. Let's comment out this stuff. I don't want to make this. That's fine. I'll leave it there. So I'm going to make another graph. Let's say G2 equals graph. I'm going to say title equals trajectory. X title equals X. Y title equals Y. Width equals 400. Height equals 400. It's a trajectory, right? I want to make them the same dimensions. And now I need something to plot. Let's just call it F1 equals G curve. Curve. Color equals color dot. Red. And dot equals true. So dot equals true is just going to make it so it animates and it's going to look really nice. It's going to look so nice. We're going to love it. So now down here, I did my plot. Now let's do some other stuff. Let's say R equals 0.6. What did I say it was? 672. That's my initial R position. I need my initial R velocity. R dot is equal to 0. I need my initial angle. Theta equals 0. I need my initial angular velocity. Actually, I don't. I can calculate that. Okay. So now I need t. I need dt. 0.01. And now I'm going to say while t is less than, let's run it for 4 seconds and find out what happens. Rate 100. So I'm putting in rate 100 because I want to animate the motion. And so that means I'm telling Python, don't do more than 100 loops per second. So it'll take 4 seconds to do the whole thing, and we can see it kind of move. It'll be fun. The first thing I'm going to do is to calculate r double dot. R d dot is equal to, I'm going to use that equation right there. I already wrote down the equation. So it's going to be equal to L squared divided by parentheses mu squared times r cubed. And so I have r, right? It's 0.672. So that I have all those values. And then minus k divided by mu, which is m. Messed up right there. M times r raised to the 5/2 power. That's r dot. Now I can use r dot to calculate r I can use, that's R double dot. I can use R double dot to calculate and update R dot. R dot plus R double dot times dt. Now I can update R. R equals R plus R dot times dt. Now I can go back over to theta. Theta dot is equal to, it only depends on R. So I can say theta dot is equal to L divided by. Should that be a 2? No. Theta dot divided by L divided by M times R squared. Now I can update theta. Theta equals theta plus theta dot times dt. Now I can calculate x and y. X equals R times cosine theta. No, you gotta spell it right. Y equals R times sine theta. Now I can plot it. F1 dot plot xy. Now I need to update time, otherwise it will run forever. T plus dt. Let's see if this thing runs. I'm not 100% sure. I haven't even saved it. You know, that's bad. Taylor, chap 8, num 25. I'll never find this again. I'll be looking for it. Like, I solved that problem that one time. What was the name of it? And I'm so bad with names. Okay. That's why I make videos. There it goes. Let's just check. One thing we can check. The minimum position, the minimum R should be, oh, it stopped. The minimum R, I think it would orbit. So let's let it run for a longer time. And let's make it run faster. So I'm going to let it run for 20 seconds. And let's run it at 3 speed, 300 rates, just to see what happens. Okay, it's coming back. Okay. It's a complicated path, and that's fine. So will it get back to that minimum position? There's a minimum position right there. I guess it should eventually get back there. But I'm pretty happy with that. I'm not going to run any more because I don't want to make any more mistakes. I think that is the correct plot. And I just want to point out how easy that is to plot. If you want to make it look even better, what you could do is go over here and say set the minimum and maximum values. So pre-scale the graph, and then it won't zoom in and out, and it looks a little bit better, but it looks pretty good to me. So I'm pretty happy. Gonna save this. Gonna give you a link to the code. If you want, it'd also be fun to make a plot right here, moving back and forth. That'd be kind of fun. I want to do that right now. Let's do that. Let's see if we can do that. Oh, no, I'm not going to do that. I'm not going to do that. You could, though. You could. Okay. I've already done enough. Did enough for this problem. I already made some mistakes. So you can make your own mistakes now. Okay, that's that. I don't have anything else to say.